A human being could stand on Venus for only as long as an extraordinary machine kept the planet from touching them. Above Jupiter, a spacecraft would enter a magnetic kingdom filled with radiation strong enough to damage electronics behind heavy shielding. Near a neutron star, gravity would pull with a violence that has no counterpart in ordinary planetary exploration, while magnetic fields could reshape matter and flood the surrounding darkness with lethal energy. A black hole would offer a quieter approach in certain conditions, followed by a boundary from which no traveler, message, or final image could ever return. Every hostile world presents a different form of death. Heat can penetrate a hull, pressure can crush it, radiation can pass through it, and gravity can tear it apart. Isolation works slowly, wearing through bodies and machines during years without shelter or rescue. Distance multiplies every danger by preventing repair teams, replacement parts, and medical assistance from arriving. The most dangerous destination may therefore be a place whose environment kills rapidly, or a place that requires travelers to survive an impossible journey before they even reach it. The ultimate limit of human exploration would lie where engineering loses the ability to create a temporary island of safety. A suit can carry air into vacuum. A pressure vessel can resist an atmosphere. Shielding can absorb part of a radiation field. Engines can hold a spacecraft above a planet and guide it between stars. Farther outward, nature begins attacking the structure of matter, the stability of time, and the causal path leading home. Somewhere between the clouds of Venus and the horizon of a black hole, exploration approaches a boundary where visiting and disappearing become almost indistinguishable. Danger begins with the human body, a warm and fragile arrangement of water, cells, electrical signals, and soft tissue shaped by one particular planet. It expects a narrow range of pressure, temperature, gravity, radiation, oxygen, and chemical conditions. Earth provides these conditions across vast regions without requiring machinery. Space offers none of them automatically. Every journey beyond Earth carries a portable fragment of the home environment, enclosed within clothing, metal, pumps, filters, and carefully controlled gases. A destination becomes accessible when a machine can preserve that fragment long enough for human beings to arrive, work, and leave. The moon has no breathable atmosphere and exposes its surface to radiation, vacuum, dust, and extreme temperature changes. These hazards remain severe, although they can be approached through shielding, suits, habitats, and short mission durations. Mars adds toxic dust, low pressure, cold, radiation, and difficult medical isolation. Its surface still permits a spacecraft to land, a habitat to stand, and an astronaut to walk beneath ordinary gravity forces. The environments farther away begin removing those familiar possibilities. Venus can destroy conventional electronics through heat. Jupiter offers no solid surface upon which a habitat could rest. A neutron star compresses a stellar mass into a sphere comparable in size to a city. A black hole removes the future paths that would allow escape. The word visit becomes increasingly strained as each destination demands a greater separation between the human and the place being explored. The ranking also depends upon purpose. Orbiting above Venus differs from landing on its surface. Passing through the outer Jovian system differs from descending beneath Jupiter's clouds. Observing a neutron star from several astronomical units away differs from approaching its magnetic poles. A spacecraft can visit the system containing a black hole while remaining far from the region where space-time becomes dangerous. The true limit appears only when explorers continue inward. Venus would look almost welcoming during the final approach. It is similar to Earth in size and mass, wrapped in pale clouds that reflect sunlight so efficiently that the planet shines brilliantly in our sky. Its gravity would feel familiar to a human body. A traveler seeing the complete world through filtered cameras might imagine oceans hidden beneath the unbroken cloud layer, continuing the ancient dream that Venus could resemble a warmer Earth. The atmosphere would begin changing that impression long before landing. Carbon dioxide dominates the air, and clouds containing sulfuric acid extend across the planet. Visibility beneath them would be limited and strange. Sunlight would weaken into an amber glow, scattered by a dense atmosphere whose lower layers contain far more material than the air above Earth. Winds high in the atmosphere race around the planet, while conditions closer to the surface become slower, heavier, and oppressively hot. A descent vehicle would feel pressure rising around it with every kilometer. The atmosphere would cease behaving like the thin gas familiar to aviation and begin resembling a dense fluid pressing against every surface. Heat would enter through the hull, forcing cooling systems to work continuously. External sensors, seals, windows, antennas, and moving parts would face chemical corrosion and temperatures capable of destroying ordinary spacecraft technology. Several robotic probes have reached the surface and transmitted briefly before failing. Their survival times were measured in minutes or hours. A human lander would need to protect a larger interior, life support equipment, scientific instruments, propulsion systems, and a crew whose return depended upon machinery continuing to operate after prolonged exposure. Every additional hour would become an engineering struggle against a planet capable of entering the vehicle through heat alone. At the surface, the temperature remains close to 465 degrees Celsius across much of the planet, hot enough to weaken materials, destroy lubricants, damage electronics, and transform the design of every mechanical system. Cooling a crew compartment would require moving heat from an already protected interior into an environment hotter than many industrial furnaces. The rejected heat would have nowhere cool to go. Refrigeration would depend upon energy-intensive systems operating with extraordinary reliability. The atmospheric pressure reaches around 90 times the pressure at Earth's surface. A conventional spacecraft cabin would resemble a low-pressure bubble submerged deep beneath an ocean. The hull would need to resist continuous compression while remaining light enough to descend and later ascend. Any defect in a seal or structural joint could grow rapidly. A failure would bring the atmosphere inward with crushing force and expose the interior to lethal heat and carbon dioxide. The ground would offer limited comfort. Venus contains volcanic plains, mountains, fractured terrain, rocks, and fine material shaped by an environment whose geology remains incompletely understood. The surface may appear motionless, although the planet's interior and atmosphere have evolved through powerful processes. A landing site selected from orbital radar would still contain uncertainties invisible before descent. A human stepping outside would wear something closer to a small pressure vehicle than a conventional spacesuit. Its rigid structure would resist the atmosphere, while active cooling protected the occupant. Joints would need to move under pressure. Cameras would replace transparent visors that might weaken or become difficult to cool. A short walk would depend upon several systems operating without hesitation inside heat, corrosive chemistry, and an atmosphere waiting to exploit every opening. Escape from Venus would add another layer of danger. A return vehicle must survive the surface environment before launching through the dense atmosphere. Fuel tanks, engines, valves, guidance systems, and ignition components would remain exposed to intense heat while waiting. Protecting them might require insulated enclosures, active cooling, or a mission architecture in which the ascent vehicle never reaches the ground. The atmosphere would resist launch through drag, although its density could also support aircraft and balloons. A crew might descend in a smaller vehicle while a larger platform remained in the upper atmosphere. The surface team would then need to rise through many kilometers and rendezvous with the platform. Any delay could consume the limited cooling capacity of the lander. A mission could avoid the surface entirely. At an altitude of roughly 50 kilometers, Venus offers temperatures and pressures much closer to those found near sea level on Earth. A breathable mixture of nitrogen and oxygen would provide lift within the carbon dioxide atmosphere, allowing enormous airships to float without relying upon highly flammable hydrogen. Human habitats could drift above the inferno while carrying protection against sulfuric acid droplets and the remaining environmental hazards. This upper region transforms Venus from an impossible surface into a conceivable aerial destination. The contrast reveals an important principle of extreme exploration. The most hostile planet may contain a narrow layer where engineering can establish safety. Human beings might one day live above a world upon which they could never walk for long. Venus would remain dangerous through chemistry, corrosion, wind, and the need to stay suspended. An airship losing buoyancy could descend into regions where temperature and pressure rose beyond its design. A slow leak would create a countdown measured by altitude. Repairs would have to be performed while the habitat continued moving through acid clouds and turbulent air. The crew would also live without a solid emergency refuge. On Earth, an aircraft can land when systems fail. A Venusian airship would float above a surface that offered no safe landing. Redundant envelopes, propulsion units, power systems, and control surfaces would need to prevent a gradual descent. Escape vehicles could rise toward orbit, although they would have to remain ready throughout the mission. Even so, the atmosphere near 50 kilometers grants engineers familiar pressure conditions and abundant surrounding gas. It provides a medium for flight, convective cooling, and buoyancy. Solar energy would be available above much of the cloud layer. The danger could be divided into technical problems with conceivable solutions. The surface remains one of the most brutal locations a human mission could attempt within the inner solar system. Its hostility arises from several forces acting together, each intense enough to challenge a spacecraft. Yet Venus still belongs to the realm of pressure vessels, cooling systems, corrosion-resistant materials, and powerful ascent vehicles. It threatens the machine without changing the laws by which the machine protects its passengers. Jupiter announces its danger before a spacecraft reaches the clouds. The planet's enormous magnetic field traps charged particles and accelerates them into belts of intense radiation. These particles strike spacecraft electronics, degrade materials, alter data, and penetrate shielding. Robotic missions survive by limiting exposure, following carefully chosen orbits, and protecting sensitive components inside armored enclosures. A human crew entering the inner magnetosphere would carry far more vulnerable material than a robotic probe. Radiation can damage DNA, increase cancer risk, injure the nervous system, affect blood vessels, and cause acute illness at high doses. Thick shielding would reduce exposure while adding mass that must be accelerated across the solar system. Some high-energy particles create secondary radiation when they strike protective material, complicating the relationship between thickness and safety. The magnetic environment changes with position and time. Jupiter rotates rapidly, carrying its magnetic field through space and interacting with particles from the solar wind and its moons. Io supplies material through volcanic activity, helping create a torus of charged particles around its orbit. A spacecraft would travel through a dynamic system filled with invisible structures capable of delivering different radiation doses over relatively short distances. Mission planners could choose safer paths. A crewed vessel might remain outside the most severe belts, sending hardened robotic craft inward. Shielded storm shelters could protect astronauts during periods of elevated exposure. Water, fuel, supplies, and waste could surround living compartments. Every kilogram of protection would need to be carried far from Earth or manufactured within the Jovian system. Approaching Jupiter itself would reveal a planet without a conventional surface. The visible clouds form the upper layers of an atmosphere thousands of kilometers deep. Beneath them, pressure and temperature rise continuously. Hydrogen changes behavior under compression, eventually entering exotic states deep within the planet. There is no quiet boundary where a spacecraft could place landing legs and begin a surface expedition. A vehicle descending into the clouds would first encounter powerful winds, turbulence, lightning, and layers of ammonia, water, and other compounds. The view would narrow as clouds surrounded the craft. Communication with orbit could weaken. Atmospheric pressure would climb, while the vehicle fell toward regions never reached directly by any human-made probe for more than a brief descent. The Galileo atmospheric probe entered Jupiter in 1995 and transmitted until pressure and heat overwhelmed it. A human vehicle would need to survive far longer and later reverse its descent. Buoyancy could support a craft at selected levels, although storms and vertical motion would complicate control. The deeper it traveled, the stronger its pressure vessel and cooling systems would need to become. Eventually, the surrounding hydrogen would compress the hull from every direction. Temperatures would rise through levels that destroy ordinary materials. The vehicle might continue falling without ever encountering a solid landscape, carried into a region where the distinction between atmosphere and fluid becomes increasingly blurred. Jupiter would consume the expedition through depth. A floating station in Jupiter's upper atmosphere could theoretically avoid the deepest pressure. It would still face gravity stronger than Earth's, fierce winds, difficult chemistry, and the radiation environment surrounding the planet. Maintaining altitude would become essential because descent would lead toward increasingly destructive conditions. Returning to orbit would demand enormous velocity. Jupiter's gravity well is deep, and a vehicle rising from the atmosphere must overcome both gravity and drag. The ascent system would need vast energy while remaining light enough to float or fly. A failure during launch could send the crew back into the clouds with limited opportunities for recovery. The atmosphere might offer useful resources. Hydrogen and helium surround the vehicle, and other compounds could support chemical or industrial processes. An advanced mission might collect fuel or study the interior through instruments lowered beneath the station. Human presence would add little scientific capability compared with robots unless the habitat could remain safe for long periods. Jupiter represents a world humans could approach closely and never truly stand upon. Exploration would occur through orbit, atmospheric flight, and remote machines. The planet's immense scale would remain physically inaccessible below a narrow range of altitude. A descent beyond that range would become a one-way journey into pressure, heat, and darkness. The moons of Jupiter offer solid ground, making them more natural destinations for human exploration. They also reveal how far the planet's radiation reaches. Io travels through an especially severe region. Its surface is reshaped by intense volcanic activity driven by tidal forces. Sulfur compounds cover the landscape, while charged particles from the Jovian environment bombard the moon. A human landing on Io would combine planetary geology with radiation exposure severe enough to dominate mission design. The crew would need heavy shielding during transit and surface operations. Habitats might be buried beneath material or placed behind massive barriers. Short excursions would still carry substantial risk. The volcanic surface could change, and plumes might rise hundreds of kilometers above the moon. Europa lies farther out and receives less radiation than Io, although its environment remains hazardous. Its icy surface may conceal a global ocean, making it one of the most scientifically compelling locations in the solar system. A human base would require protection from charged particles, extreme cold, vacuum, and the possibility of contaminating an environment that could contain life. Callisto orbits beyond the most intense radiation belts and has often appeared in studies as a safer base for exploring the Jovian system. From there, crews could direct robots toward Jupiter, Europa, and Io while remaining in a more manageable environment. The choice illustrates how human exploration naturally retreats from the most dangerous place to a nearby refuge. Jupiter's danger can be reduced through distance because radiation intensity and gravitational risk change dramatically across its system. A spacecraft can remain in a safer orbit, observe the planet, and return home. A crew can establish a base on a distant moon while sending machines into the inner magnetosphere. Human survival depends upon respecting an invisible boundary drawn by radiation dose and available shielding. The planet itself becomes fatal gradually during descent. Pressure does not leap from tolerable to impossible at one clear surface. Each kilometer removes engineering margin. The final point of failure depends upon the vehicle's design. A stronger craft can descend farther while no material structure can continue indefinitely. This gradual progression makes Jupiter an ideal symbol for the limit of planetary exploration. A crew could always travel slightly deeper with improved technology. Each improvement reveals another region where pressure and heat continue rising. The planet offers no triumphant landing, only a record depth followed by ascent or destruction. Yet even Jupiter remains governed by familiar forms of stress. Radiation deposits energy. Pressure applies force. Heat moves through material. Gravity determines trajectories. The challenge may exceed any technology humans eventually develop, although the mechanisms can be measured and modeled from outside. Interstellar space appears peaceful after Venus and Jupiter. Far from planets, a ship would encounter an environment of extraordinary emptiness. No crushing atmosphere would press against the hull. No nearby world would pull the vehicle downward. Stars would shine as distant points, and the surrounding gas might contain only a few particles within a volume that would hold countless molecules on Earth. The danger of interstellar space comes from duration and exposure. Galactic cosmic rays travel through the galaxy with energies capable of penetrating spacecraft and damaging living tissue. Solar storms would fade as the ship left the sun, although cosmic radiation would remain. Shielding could reduce the dose, and a voyage lasting decades or centuries would allow small biological injuries to accumulate. Dust grains become dangerous at high speed. A particle almost too small to see can strike with tremendous energy when the spacecraft moves at a significant fraction of light speed. The forward hull would endure a continual stream of atoms and occasional larger impacts. Thick shielding, magnetic fields, sacrificial material, and advanced detection systems could provide protection, each adding complexity and mass. The ship would also lose access to external resources. Between stars, there may be no nearby world from which to obtain water, metals, fuel, or replacement parts. Every useful object must be carried, manufactured, or recycled. A minor shortage on a planet can be resupplied. The same shortage halfway to another star becomes a permanent condition. Medical isolation would be absolute. A crew member suffering a rare illness could not be returned to Earth. No specialist could travel to the vessel. Communication delays would grow from hours into years, turning advice into correspondence. The ship would need laboratories, medicines, surgical capability, diagnostic systems, and enough trained people to respond locally. Mechanical failures would carry the same finality. A spacecraft could contain redundant engines and workshops, though every system depends upon other systems. A damaged manufacturing machine may prevent the production of parts needed to repair life support. A software failure may affect equipment whose original programmers died decades earlier. The mission would survive through an industrial chain operating inside a moving container. Psychological danger would grow through monotony and irreversibility. The crew would see no changing landscapes, weather, cities, or natural horizon. The destination might remain a bright point for most of the journey. Every person would know that leaving the ship meant death, and turning around might offer no practical rescue. Interstellar space kills slowly enough to permit an entire society to observe the approach of failure. Radiation raises future disease risk. Materials degrade, skills disappear, trust weakens. A sudden catastrophe may never occur. The ship can become less capable each year until one ordinary fault exceeds the remaining ability to respond. For a short mission, empty space may be safer than the surface of Venus. For a voyage lasting centuries, it becomes a test of whether any closed human system can remain healthy, motivated, and technologically competent. The surrounding vacuum serves as a permanent consequence for every internal mistake. A habitat on Mars could lose a crop and receive supplies from another settlement. A vessel between stars has only its reserves. A political conflict on a planet can lead people to migrate. A conflict inside a generation ship remains enclosed with the air and water shared by every faction. Distance converts technical, biological, and social weaknesses into existential risks. The interstellar void may therefore cause fewer immediate deaths while presenting one of the lowest overall chances of mission success. Its hostility lies in the absence of anything capable of helping. It provides no pressure, no warmth, no food, no raw material conveniently gathered, and no second opportunity. Still, a ship can carry a habitable world through the void. Artificial gravity, thick shielding, nuclear power, closed agriculture, autonomous medicine, and internal manufacturing could transform empty space into a navigable ocean. The engineering burden would be immense, although the environment would remain quiet enough for the vessel to build its own conditions. A neutron star belongs to a different category of destination. It forms when the core of a massive star collapses during a supernova and compresses a mass comparable with the Sun into a sphere only a few tens of kilometers across. Matter reaches densities so extreme that a small quantity would possess a weight inconceivable under Earth gravity. The surface gravity can reach tens or hundreds of trillions of times the gravity experienced on Earth, depending upon the star's mass and radius. A human body could never stand upon such a surface. The difference in gravity between the feet and the head would stretch tissue, disrupt circulation, and destroy structure long before the traveler experienced anything resembling a landing. The surface itself would be composed of matter crushed into states unavailable under ordinary planetary conditions. Atomic nuclei, electrons, and deeper layers containing neutrons or more exotic arrangements would form an extraordinarily rigid and dense object. A spacecraft touching it would arrive at immense velocity under gravity, releasing catastrophic energy. Landing gear has no meaning in this environment. Engines capable of hovering would need to counter a gravitational field that accelerates matter toward a substantial fraction of light speed. The energy required to descend gently and later climb away would be enormous. A small navigation error could become unrecoverable within moments. Gravity would begin threatening the spacecraft well above the surface. Tidal forces arise because the near side of an object feels stronger gravity than the far side. Around a neutron star, this difference can become extreme across the length of a ship. The structure would be pulled unevenly, creating stress through the hull and every connection inside it. Time would also pass differently near the star compared with distant observers. Light climbing away would lose energy and appear redshifted. The crew's clocks would remain normal to them while observers farther away measured another rate. Navigation would require relativistic calculations, especially during a close orbit. A quiet neutron star may emit less radiation than a pulsar or magnetar, offering a comparatively manageable target at sufficient distance. Comparatively manageable still leaves gravity, residual heat, high-energy particles, and the legacy of the stellar explosion that created it. The approach would be planned around a region where observation remains valuable and escape remains possible. Robotic probes would precede any human mission. They could measure the magnetic field, map radiation, and test trajectories. A crewed spacecraft would likely remain far away, using telescopes and remote instruments. The closer probes traveled, the more the mission would resemble sending expendable devices toward a natural accelerator. Many neutron stars rotate rapidly and carry powerful magnetic fields. When beams of radiation sweep across space with each rotation, distant observers detect regular pulses and describe the object as a pulsar. Some complete many rotations every second. Their surroundings contain electric fields, charged particles, X-rays, gamma rays, and electromagnetic processes capable of accelerating matter to extraordinary energies. A spacecraft approaching along an unfortunate direction could enter a beam of intense radiation. The pulses would arrive with precise timing, striking the hull repeatedly. Shielding that protects against ordinary deep space exposure might offer limited defense against concentrated high-energy emissions. Electronics could fail while the crew received a lethal dose. Magnetars carry even stronger magnetic fields. Near the star, such fields can influence atomic structure and the behavior of matter. Powerful outbursts can release enormous amounts of high-energy radiation. A human mission would require a safety distance measured according to the field, the star's activity, and the possibility of events that cannot be predicted perfectly. Magnetic fields decline with distance, allowing a spacecraft to observe from a remote orbit. Every step inward would raise the scientific value and the danger. A probe close enough to study the surface in extraordinary detail might enter a region where materials, electronics, and human tissue behave in unfamiliar ways. A neutron star system could still be visited in the broad astronomical sense. A crew might enter orbit around a companion star, remain far from the compact object, and operate robotic observatories. Binary systems can contain streams of gas pulled from one star toward the neutron star, producing luminous X-rays in unstable conditions. A solitary, quiet neutron star would provide a cleaner target. The mission would need to navigate around gravity with exceptional precision. Escape remains physically possible outside the star, provided the spacecraft retains enough velocity and propulsion. There is no event horizon surrounding an ordinary neutron star. Light and matter can leave its surface, although the climb costs enormous energy. This distinction preserves the meaning of return. A spacecraft can approach, observe, alter course, and carry its data home. The practical safe distance may remain thousands or millions of kilometers from the surface. The visit would resemble an expedition to the outskirts of a storm whose center could never contain a human vehicle. Calling the neutron star itself accessible would therefore require a generous interpretation. Humans could reach its neighborhood. Instruments could descend closer. The surface lies beyond every plausible form of direct exploration because gravity, radiation, and impact velocity converge there. A black hole can appear less violent from far away. It is defined by mass compressed within a region whose escape boundary is the event horizon. Outside that horizon, gravity follows predictable laws. At a sufficient distance, a spacecraft can orbit a black hole in the same manner that planets orbit stars, adjusted for the mass and nearby matter. Black holes vary enormously. Stellar mass examples may contain several times the mass of the Sun within a horizon only tens of kilometers across. Supermassive black holes can hold millions or billions of solar masses, with horizons spanning millions or billions of kilometers. Their scale changes the tidal forces experienced near the boundary. The black hole itself may be dark. Most danger visible from great distances comes from matter around it. Gas falling inward forms an accretion disk, heats through friction and compression, and can radiate across the electromagnetic spectrum. Magnetic processes may produce jets that extend far beyond the central region. A feeding black hole can become one of the brightest and most energetic objects in the universe. A quiet black hole with little surrounding matter offers a different destination. It could be approached without flying through a brilliant disk of plasma. The darkness would be revealed through the motion of nearby stars, the bending of background light, and the distortion of the sky around the horizon. An active black hole would likely kill a human crew through radiation before gravity became the central problem. The inner accretion disk can reach extreme temperatures and produce X-rays. High-energy particles and magnetic fields fill the region. Jets, when present, can carry energy across enormous distances along the rotational axis. Approaching through the plane of the disk would expose the vessel to hot plasma moving at relativistic speed. Matter may be sparse by terrestrial standards, while each collision carries immense energy. Heat and radiation would overwhelm shielding. The environment changes rapidly as turbulence, magnetic fields, and orbiting material interact. Approaching along the axis could avoid the densest disk and lead directly into a jet. The safest trajectory would depend upon detailed observation of the black hole's activity and orientation. A system considered quiet during planning could change if new material began falling inward before the crew arrived. The black hole's danger would therefore begin far outside the event horizon. A luminous galactic nucleus could remain lethal across distances comparable with a planetary system. Human exploration would require a dormant object, isolated enough to avoid a dense disk and weak enough in radiation to permit approach. A stellar mass black hole would create strong tidal forces near its horizon because its gravity changes sharply across short distances. A falling astronaut could be stretched along the direction of descent and compressed from the sides before reaching the boundary. The process is often described as spaghettification, a name whose humor conceals the destruction of every biological structure. A supermassive black hole has a much larger horizon. The gravitational gradient at that horizon can be gentler, allowing a traveler to cross without experiencing immediate tidal destruction. A person falling through the boundary of a sufficiently massive and quiet black hole might detect no local surface or sudden impact at the crossing itself. The absence of immediate destruction would make the event more disturbing. Outside observers would see the traveler's signals become delayed, dimmed, and redshifted. The falling person would continue inward according to their own time. Once the horizon had been crossed, every future directed path would lead deeper into the black hole. The crew could survive the crossing briefly and lose every ability to report what followed. Light emitted inward could not climb back across the horizon. A final message sent too late would remain trapped with the sender. Exploration would continue for the traveler and end for the rest of humanity at the same boundary. A flyby near a black hole could avoid crossing the horizon. The spacecraft might pass through a carefully calculated trajectory, observe gravitational lensing, measure space-time effects, and then escape. The closer the approach, the greater the energy required to control the path and the smaller the margin for error. Stable circular orbits exist outside black holes, though their innermost location depends upon the hole's rotation and the direction of orbit. Inside the innermost stable circular orbit, maintaining a long-term path becomes impossible without continuous acceleration. Matter tends to plunge inward. A crew traveling there would rely upon engines to resist a geometry that no longer supports a stable orbit. Rotation complicates the environment through frame dragging, where space-time itself is carried around the spinning black hole. The ergosphere outside the horizon of a rotating black hole permits processes that can exchange energy with the object's rotation. Advanced civilizations might imagine extracting energy there, although a human mission would face navigation and radiation challenges of extraordinary precision. A quiet, supermassive black hole would offer the most survivable version of this expedition. Its large scale reduces tidal gradients near the horizon. The spacecraft could approach through a region with little surrounding gas. The central danger would come from trajectory, propulsion, and the irreversible boundary ahead. Time near the black hole would separate the crew from distant observers. A spacecraft maintaining a position or orbit close to the horizon would experience time differently from people far away. The exact effect would depend upon motion, gravity, and the chosen trajectory. Messages would arrive distorted and delayed. The crew could spend a limited period near the black hole while a longer interval passed elsewhere. Returning home might mean returning to a future whose people and institutions had changed. Extreme exploration would therefore threaten the traveler's place in history even when their bodies survived. Holding position close to the horizon would require tremendous acceleration. A freely falling spacecraft experiences weightlessness while moving inward. Remaining fixed above the boundary requires engines to oppose gravity, and the required acceleration grows without limit as the horizon is approached. No finite engine can hover exactly at the boundary. The practical expedition would follow an orbit or flyby, accepting motion around and past the black hole. Its closest approach would be selected through the energy budget and desired safety margin. The horizon could be observed as a dark region shaped by gravitational lensing, always near enough to dominate every decision and far enough to preserve a path home. The event horizon creates a boundary unlike the surface of Venus or the atmosphere of Jupiter. A stronger hull offers no protection after crossing. Additional fuel cannot provide escape. A faster signal cannot outrun the causal structure of space-time. The problem no longer concerns the durability of the vehicle. An astronaut descending toward Venus can still launch upward if the ascent system works. A probe falling into Jupiter can theoretically escape before reaching sufficient depth if it retains enough thrust. A vehicle approaching a neutron star can alter course outside the surface. Beyond a black hole's horizon, escape disappears from the set of possible futures. This makes the horizon the ultimate physical boundary of travel. It can be crossed inward, giving it the character of a destination. It cannot be visited in the ordinary sense because visiting contains an expectation of departure. Crossing changes the expedition into a final transmission whose conclusion remains inaccessible. A human mission might deliberately send a volunteer through after completing observations outside. The act could produce measurements until the last signal escaped. The person would continue beyond that final message, carrying experience that would never become shared human knowledge. The The deepest stage of the mission would exist only for the traveler. Comparing these destinations requires separating lethality from extremity. The surface of Venus could kill through heat and pressure within moments after protection failed. Jupiter's inner system could deliver lethal radiation while the planet's atmosphere crushed any descending vehicle. A neutron star could destroy a spacecraft through gravity, radiation, and magnetic fields. An active black hole could sterilize the crew from far outside its horizon. Interstellar space may produce the highest chance of mission failure because it extends every vulnerability across decades or centuries. Its emptiness offers no single dramatic force, yet it allows radiation, mechanical decline, biological stress, and social conflict to accumulate. A crew might survive a short passage near a dangerous planet and fail during the quiet journey required to reach it. The most hostile environment and the most difficult mission can therefore be different. Venus provides concentrated planetary hostility. Interstellar space provides prolonged exposure. A neutron star provides an environment that cannot be entered closely by ordinary matter without devastating consequences. A black hole provides a boundary where return becomes physically impossible. Human exploration would approach each place through layers of distance. Orbiters would precede landers. Robots would travel ahead of crews. Remote instruments would descend where people could not. The final human position would be determined by the nearest point at which a habitable machine could still preserve a route outward. If survival and return remain essential, the most dangerous destination humans could visit may be the inner neighborhood of a quiet, supermassive black hole. The hole would need to lack a bright accretion disk and powerful jet. Its mass would need to be large enough for tidal forces near the horizon to remain survivable. The spacecraft would approach the innermost region while preserving an escape trajectory. No planet offers comparable control over spacetime. Background stars would bend into distorted arcs. Light could circle the black hole before entering the cameras, creating multiple images of the same region. The crew would watch the external universe transformed by gravity and motion. The horizon would remain ahead as a boundary that instruments could map without touching. Every calculation would contain a margin preventing accidental capture. Engine failure, navigational error, collision, or unexpected matter could push the craft onto an inward path. Rescue would be limited by the same geometry threatening the crew. This expedition would bring humans close to a region where the known description of nature reaches its most severe form. They could observe the border while remaining outside it, carrying their measurements home. The mission would turn the phrase edge of exploration into a literal property of spacetime. A neutron star could compete for the title through the violence of its accessible environment. A magnetar's radiation and magnetic field may establish a lethal boundary far from the surface. Approaching closely enough to experience the most extreme conditions would likely destroy the crew before any meaningful orbit could be completed. The black hole offers a narrow and counterintuitive advantage. A dormant, supermassive example can possess a relatively calm environment outside its horizon. Gravity becomes extreme, while local conditions remain survivable along carefully chosen paths. The journey would still require technologies capable of crossing immense interstellar distance and navigating with precision beyond current imagination. An active, supermassive black hole would remove that advantage. Its disk and jets could make the wider system more lethal than the horizon itself. The scientifically perfect target would therefore be an almost invisible black hole, detectable through gravity and surrounded by little material. The most dangerous place humans could ever reach may consequently appear quiet. There may be no flames, surface, storm, or explosion. A dark region would occupy part of the sky while the stars around it bent into unfamiliar patterns. The danger would exist inside the shape of every possible trajectory. Long before such a mission, humanity would need to master the less exotic dangers. Venus would teach us to preserve machinery in heat and corrosive atmospheres. Jupiter would demand protection against radiation and deep gravitational wells. Interstellar voyages would require closed ecosystems, autonomous medicine, and machines capable of repairing themselves across generations. Each destination would prepare explorers for the next by removing another dependence upon Earth. Planetary missions would teach crews to survive without immediate rescue. Generation ships would teach societies to remain coherent through long isolation. Neutron star observatories would require relativistic navigation and extraordinary shielding. Black hole exploration would combine all these capabilities near a boundary with no forgiveness. The progression would extend across centuries or millennia of technological and cultural development. The humans approaching a black hole might differ biologically from people alive today. They could use artificial bodies, advanced genetic protection, digital consciousness, or forms of shielding that remain speculative. The word human might describe ancestry and identity more clearly than physical vulnerability. Even transformed explorers would remain subject to the event horizon. Technology can change the traveler. It cannot create an outward path where space-time provides none under known physics. The mission's final approach would begin after years in the target system. Robotic probes would map radiation, gas, dust, magnetic fields, and the black hole's rotation. Telescopes would observe matter moving around the central darkness. Every measurement would refine the safe corridor. The crewed vessel would release additional probes during descent. Some would enter unstable orbits and fall inward, transmitting until their signals weakened beyond recovery. Others would remain outside as navigation references and communication relays. The human ship would proceed only after each layer of the environment matched the models. Inside, the crew would feel no mystical pull. Local gravity during free fall would produce weightlessness. Instruments would reveal the growing curvature through changing trajectories, distorted light, and differences between clocks. The horizon would become apparent through calculation and imaging rather than a visible wall. The absence of a physical barrier would demand discipline. A planetary cliff announces its edge. The horizon conceals its finality inside geometry. The crew could cross without impact and discover the mistake only when every attempted escape trajectory continued inward. At the closest planned point, engines would guide the spacecraft through a path carrying it around the black hole and outward. The maneuver might use the object's gravity to change direction or speed. Every component would operate against strict timing. A delayed burn could remove the path home. The external universe would appear compressed, magnified, and duplicated by gravitational lensing. Light from regions behind the black hole would curve around it. The crew could see altered images of the galaxy and perhaps light that had traveled along several paths before reaching them. Scientific instruments would measure gravity under conditions unavailable anywhere else. They could test relativity, study the horizon's surroundings, and search for subtle effects pointing toward a deeper theory. The expedition would explore a place where gravity, quantum physics, and information meet unresolved questions. Then the craft would climb away, the darkness would shrink. The bent star field would relax gradually into familiar geometry. A signal announcing survival would travel outward toward distant humanity, carrying knowledge gathered close to the last boundary from which knowledge can return. The event horizon itself would remain unvisited by anyone who came home. Its crossing could be recorded only from the outside until the final outward signal. Every human account would end before the deepest part of the fall. This creates an unusual limit to exploration. A mountain can be climbed and described. An ocean trench can be entered and left. Venus might permit a brief surface expedition inside an extraordinary vehicle. Jupiter's clouds could be sampled through expendable probes. A black hole allows entry and removes the return required to complete the story. The ultimate boundary may therefore depend upon whether exploration requires communication. A person crossing the horizon would physically reach a region no human had entered. Humanity would receive no direct account of what happened afterward. The event would enlarge the territory touched by a human while adding almost nothing to shared experience beyond the measurements transmitted before crossing. An expedition designed around return would stop outside. A journey designed around reach could continue inward. The distance between those objectives might be only a short interval for the falling traveler and an absolute division for everyone else. Venus would burn and crush the unprotected body. Jupiter would irradiate it and pull it into an atmosphere without ground. Interstellar space would expose it to years of radiation, isolation, and mechanical dependence. A neutron star would subject it to gravity and fields capable of destroying matter's familiar organization. Each place defines a distinct edge of survival. The black hole defines the edge of return. Its danger can remain invisible, and a sufficiently large example may allow a person to cross the horizon alive. The fatal property lies in the future. Every path that once led outward has disappeared. For this reason, the most dangerous place humans could ever visit would be the immediate vicinity of a quiet, supermassive black hole, as close to the event horizon as a spacecraft could travel while preserving a viable escape. It represents the last region where exploration can still produce survivors, witnesses, and knowledge carried home. A few kilometers, seconds, or decisions farther inward, depending upon the black hole's scale and the vessel's path, the mission would acquire another meaning. The crew would cease traveling toward a destination from which they could return. They would enter a part of the universe that could receive them and could never release their answer. Perhaps no biological human will ever make that approach. Machines may explore first and remain the only travelers considered expendable enough to cross the final boundary. Artificial minds could transmit their observations while falling, continuing beyond the last message inside bodies designed for radiation and acceleration. Yet the human desire behind the mission would remain recognizable. Every expedition begins with the belief that the unknown deserves to be approached, measured, and carried into shared memory. Venus, Jupiter, neutron stars, and black holes differ in scale, although each forces the explorer to decide how much risk knowledge can justify. The limit would move as technology improved. Better cooling would extend survival on Venus. Stronger shielding would permit deeper entry into Jupiter's radiation belts. Faster and more autonomous ships would reduce the danger of interstellar space. Advanced materials and propulsion would allow closer observation of neutron stars. The horizon would remain. It would wait beyond every engine and shield, a boundary created by space-time itself. Human capability could approach it with increasing precision while leaving its fundamental condition unchanged. One day, a spacecraft may hang above the clouds of Venus while surface vehicles work below. Human stations may orbit Jupiter from protected distances, sending machines through storms and radiation. Interstellar vessels may carry living communities toward nearby stars. Observatories may study neutron stars closely enough to reveal the behavior of matter compressed beyond anything known on Earth. Farther in the future, another vessel might enter orbit around a silent black hole. Its crew would watch the universe curve around an absence whose gravity dominates the sky. They would know that the most dangerous part of the mission contained no ground to collapse, atmosphere to ignite, or storm to cross. Their survival would depend upon remaining on the correct side of an invisible line. Every instrument could point inward. Every probe could descend. The crewed vessel would preserve one final requirement: a future trajectory leading away. That path home would define the boundary of human exploration. Beyond it lay territory a person could enter and humanity could never hear described. The most dangerous place would therefore be measured through possibility. A place becomes explorable while a traveler can arrive, observe, and leave. Venus approaches the limit through temperature and pressure. Jupiter approaches it through radiation, gravity, and depth. Interstellar space approaches it through duration. A neutron star approaches it through the concentration of stellar mass and magnetic energy. A black hole gathers danger into geometry. Outside the horizon, the universe still offers choices. A spacecraft can orbit, accelerate, turn, and transmit. Inside, all choices point toward a deeper interior. The boundary contains no mercy because mercy would require an available direction. Human beings may eventually reach that edge after surviving environments that seem impossible today. The achievement would show that intelligence can carry a small region of life through vacuum, radiation, crushing gravity, and interstellar time. The final limit would remain where the route home ends. Close enough to see the darkness bend the stars, the explorers would encounter the most dangerous place a human could ever visit and still return to tell us that it was there.